Hi everybody, and welcome to the conclusion of Chapter 15 of the video on Section 15.3. In this video we talk about measuring spread of data. So remember in Section 15.2 we looked at things like the mean and the median, and these numbers were trying to tell you where the center of the data is, trying to tell you how a typical student does on an exam, for example. Okay, but the mean and median, since they only measure the center of the data, they can't tell you much else. So in particular, here are two different data sets. This first data set is just 75s, 6 of them, and the next data set is 50, 60, 70, 80, up to 100. And let's suppose that each data set represents exam data. Now I could ask you, this first section here of students, these 6 students, what was the average score? What was the median score? And you would come back with an answer of 75. Okay, the average and median here are just 75. I can ask you the same thing about the second section of exams, the 6 students here. What's the average? What's the median? And you would say the same thing. The average and the median are both 75. So if all you're going to do is look at means and medians, these two data sets are the same from your perspective, right? The mean and the median tell you the same thing. Sort of a typical student got a 75. However, these data sets are wildly different, right? If they represent exam data, the performances of the two separate courses is far different. So in this first course here, everybody got a C. Okay, so at least nobody failed, but nobody got above a C, right? So that's sort of depressing. In the second section here, a couple of people did really well, right? 90 and 100. And then this guy right here did very poorly, right? There's actually an F in this section. So the mean and the median by themselves can't really tell you how the data is spread out, right? This first section of exams here, the data is not spread out at all. It's just all the same number. This data set, on the other hand, the data is spread out, right? It ranges from 50 to 100, and you have numbers going by tens all the way up to 100. So if you really want to get a hold of what a data set looks like, you can't just look at the mean or the median, because all that's going to tell you is where the data is centered. You also need some sort of measure of how spread out the data is. So that's what section 15.3 is about. Okay, so the most naive way and the most crude way to do this, if you want to measure spread, is simply to take the difference of the highest and lowest values in the data set. And this number is called the range. So the range is just the biggest number minus the smallest number. Okay, and the range can be useful. It's just as kind of crude because it only depends on the biggest and smallest numbers. Right, so you could have a data set with millions of numbers in it, and the range would just be the biggest one minus the smallest one. It won't tell you anything else about what's happening in between. So, like I said, the range is fairly crude. So in these two examples here, in the first data set, the range is 0. The biggest number is 75, as is the smallest number. So when you take 75 minus 75, you get 0. So this first data set here has a range of 0. This next data set has a range of 50, because 100 minus 50 is 50. So in this small little toy example here, the range did tell you something. It told you, man, this first data set is not spread out at all. The distance from the smallest to the biggest number is 0. So if the range is 0, you know that the data is just all the same number. But in this example here, we learned, oh, there actually is some spread because we have to go at least from 50 to 100. Now again, in this data set right here, I could change these intermediate numbers to whatever I want. I could change the 60 to a 65, the 70 to a 63, whatever. And the range won't change as long as these numbers stay between 50 and 100. So again, the range only tells you the distance from the smallest number to the biggest number. So it's kind of a crude measure of spread. And as the slides here point out, if you have outliers, the range can be distorted quite easily if you're trying to measure spread. So here we harken back to the example that has been running through section 15.1 and 15.2, the range of the test scores in that Stats 101 exam. So remember that those scores ranged from 1 all the way up until 24 for, for an actual range of 23 points. Biggest score minus smallest score is 23, which indicates that there's a big spread, because remember, this exam was graded out of 25 points. So the range here is almost equal to the total number of possible points. So if all I told you was, oh, the range is 23, you might conclude, wow, that's a lot of spread. This data must be really spread out. Okay, but remember that this data set had two outliers. This 24 and this 1 were both outliers. And so if you throw those outliers away, the remaining 73 students only have a range of 10. Okay, so we cut the range by more than half simply by throwing out some outliers. And again, a range of 10, a spread of 10, is not nearly as big as a spread of 23. Okay, so again, the range is kind of crude. It will just tell you the distance from smallest to biggest, and so sometimes that number can give you a distorted view of how spread out the data is. Okay, so a different kind of range is called the interquartile range. So remember here, let's go back, the range is the distance from the smallest number to the biggest number inside your data set. So you just take your biggest number minus your smallest number. The interquartile range measures the difference from the first quartile to the third quartile. And so remember that half of the data lives between Q1 and Q3, and 25% lives below Q1, and the other 25% lives above Q3. So the interquartile range is trying to tell you how spread out the middle half of the data is. Okay, so again though, the interquartile range is just a difference of two numbers. It's just measuring Q3 minus Q1, which is just the distance from Q1 to Q3. Okay, so the 5-number summary for the 2007 SAT math scores, remember this is an example that we looked at in section 15.1 and 15.2. Okay, so the minimum score was 200, and if you don't know how this works, you get 200 just from the get-go on the math section. Okay, so like basically if you write your name down, you'll get a 200. So there were some people who missed every question, and then the first quartile was 430, the median was 590, and the biggest number was 800. Okay. So the range was 600. Oops, sorry, there's a typo here. This should be Q3 is 590. Sorry, not the median. Q3 was 590. That's what we found out when we looked at this example previously. So the first quartile was 430. The third quartile was 590. Therefore, the interquartile range is 160. So you've learned that the sort of middle half of the students ranged from 430 to 590. So the total distance there is 160. So the range is really big, right? The range was 600 points. But the interquartile range was not nearly as big, right? It's less than a third of the overall range. So the middle cluster of students wasn't nearly as spread out as the overall distribution of students. Okay, so range and interquartile range, you will see them show up in statistics literature. Okay, they have some use, but as I've said multiple times now, they are crude measures because they only take into account two numbers. So for the range, you just do biggest minus smallest. For interquartile range, you simply do third quartile minus first quartile. Okay, but there are lots of other numbers in these data sets, right? And they can be going all over the place. And you're not going to be able to detect all sorts of fluctuations in between the biggest and smallest values without some other more sophisticated measure of spread. So all that being said is, the standard way to measure spread in a data set is called the standard deviation. This is a much more sophisticated measure of how spread out data is than the range or the interquartile range. So the key concept for understanding the standard deviation is deviation from the mean. Okay, so what standard deviation is trying to tell you is, it's trying to tell you the average distance of your data points from the mean. So it's measuring spread about the mean. Okay, so the idea here is that if you can measure the average distance from the mean, then you can measure spread. But keep that in mind. That's what the standard deviation is trying to tell you. It's trying to tell you how spread out the data is, but in particular, it's trying to tell you the average distance from the mean for all of the data points. Okay, so the distances from the mean are themselves another data set which we would like to summarize. And one way we could do that is to average all of those. But if we do that, negative deviations and positive deviations will cancel each other out. Okay, so you don't want to have negative numbers when you're calculating distances from the mean, because you can have positive stuff canceling out with negative stuff and getting you a skewed answer. So what we're going to do to take this into account, that we don't want to have negative distances, is we're going to square things. Because when you square things, you always make negative things positive. Okay, so -1 times -1 is +1. -2 times -2 is +4, etc. So that's what we're saying here, that we don't want to have sort of negative distances from the mean. So let's just square everything we see, because when we square things, we will make things positive, and we won't have positive-negative cancellation. Okay. So the squared deviations are never negative. If we average them out, we get an important measure of spread called variance. And, well, I don't know what this is here. Okay. But for us, we'll just denote the standard deviation with SD. So once you have the variance, you take its square root, and you will get the standard deviation. Okay, so the following is an outline of the definition of standard deviation of a data set. So let's look at the definition. So let's let A be the mean of a data set. Okay, so notice from the get-go, you have to know the average of your data set before you do anything. So the first step here, if you don't know the average, is to calculate it. So let's let A be the average of the data set. For each number x in the data set, compute its deviation from the mean, which is simply the difference of your number from the mean. So for every number inside your data set, you're going to compute just number minus average, number minus average. But as we discussed earlier, suppose that x is 2, but the average is 7. 2 minus 7 is -5. And as we discussed earlier, you don't want to have negative distances floating around. So once you compute number minus average, square that number to get a positive number. So once you've done that, that's called squaring the deviations. Then what you do is you find the average of the squared deviations, and then take the square root of that. Okay, so we'll do an example in a second, but this is the global idea here. For each number in your data set, you're going to sort of measure how far that number is from the mean. And then you're essentially going to average those distances. And when you do that, you get a measure of spread. Okay, the more spread out your data set is, the bigger these differences are. Right? So the more spread there is in your data set, the farther things will be on average from the mean. And so then when you compute the average of these deviations, you get something bigger the more spread out your data set is. Okay, so let's do an example. So over the course of the semester, Angela turned in all of her homework assignments. Her grades in the 10 assignments, and we've already sorted them, they go from 85 to 95, right? So the range here is 10. We get that immediately. Our goal in this example is to calculate the standard deviation of this data set. And let's just do it by hand, essentially. So the first thing we need is to calculate the average, right? So as I pointed out on this slide, you need the average before you do anything. So we've already calculated it for you here. The average is just 90. Okay, you can confirm this on your own. So armed with the average, the next thing we do is we take every single number in our data set and subtract the average from it. So we do 85 minus 90 is -5. 88 minus 90 is -2, etc. Okay, so again, what's happening here is the data set consists of 10 numbers. Once you have the average, you subtract the average from all of those 10 numbers. So 85 minus 90, 86 minus 90, 87 minus 90, etc., all the way up to 95 minus 90. And you get a list of distances from the mean. But again, we don't want to have positives and negatives canceling out here. So we don't want to have this -5 canceling with this +5. So the next thing we do is we square every number that we see. And -5 times itself is +25. -4 times itself is +16, and so on. So this list here is a list of squared distances from the mean. And once we have this list, we simply average that list and compute the square root of that. So this V here is the average of this list. If you average all of these numbers, you get 11. So once you've averaged these numbers, you take the square root of the result. So we got a V value of 11. So the final thing we get here, the SD or the sigma, you can use either letter, is 3.3 or so. Okay, so basically let's just go back to this data set here. What we're basically saying is, and this is all in quotes, okay, this is not exactly what we've done, but it's the idea. We have now discovered that the, quote, average distance from the mean, end quote, is about 3.3. And that is now a measure of spread. Okay, so the mean is right here, right at 90. So some numbers are close to the mean, like 89 and 91, but other numbers are farther from the mean, right, like 95 and 85 are farther. So when you sort of take into account all the different distances and average those out, you get something around 3.3. Okay, so here's a standard deviation calculation. But putting the calculation itself aside, you really need to keep in mind the big picture. This standard deviation number is a measure of spread. So the higher this number gets, the larger this number gets, the more spread out the data set is. So suppose that I took this data set and I said, oh, sorry, this 95, that was a typo. It was actually a 100. This 85, sorry, that was a typo. It was actually a 65. So if I make those two changes, the data becomes more spread out. And so without even calculating anything, you know ahead of time that if now you were to calculate a new standard deviation, that new standard deviation should be bigger than 3.3. Okay, because I took a data set with standard deviation 3.3 and I made that data set more spread out. Okay, so this number, again, is a number of spread. How spread out is this data set? So the more spread you have, the larger this number gets. Okay, so let's just make that more concrete now, interpreting that number. It's clear from just a casual look at her homework that she was pretty consistent, right? So basically 90 was kind of right in the middle of what she did, and sometimes she got a little above, sometimes she got a little below, but she was pretty consistent with her scores. So she basically was pretty close to 90 all of the time. So the standard deviation is, in effect, a way to measure how consistent the scores are. So the more consistent the scores are, the less spread there is. And on the other hand, the more inconsistent you are, so if the scores are all over the place, the higher the standard deviation will be. So a small standard deviation tells us that the data is consistent and the spread is small. But on the other hand, a large standard deviation would tell you that the data is not consistent and that the spread is large. So the data would be all over the place. Okay, so one extreme you could consider is, what if somebody gets the same score? Right? So Angela, she got different scores, right? But suppose that all 10 of these scores were a 20. That's what this is saying here. So Chloe didn't do very well. She got a 20 on every single homework. So I give you the conclusion right here that the standard deviation is 0. But again, think this through. Without even calculating anything, you could predict that the standard deviation is 0. Because in Chloe's case, all of her numbers are the same. There is no spread. the mean is 20 and the average distance from the mean is 0, right? The distance from the mean is always 0. So if the data set consists of numbers that are all the same, that means there is no spread, which means the standard deviation would be 0. Okay, so a standard deviation can never be negative. Okay, a -5 standard deviation doesn't mean anything. The lowest a standard deviation can get is 0, and you have a standard deviation of 0 when your data points are all the same, when everything is perfectly consistent and therefore there is no spread. On the other hand, if you have scores that jump all over the place, you should expect to get a larger standard deviation. So Chloe was consistent, but not in a good way, right? She was consistently low. So Tiki here is inconsistent, and sometimes he does well, like 85 and 95, but sometimes he does very poorly, right? 5 and 15. But the point here is that these scores jump all over the place, right? They range from 5 to 95, and you count by tens every time. So since there's a lot of spread here, we should expect the standard deviation to be big. And if you calculate it the way we just calculated Angela's standard deviation, you would see that this is indeed the case. So Tiki has a standard deviation of 29 points. This is in contrast to Angela's standard deviation of 3.3 points. Okay, his scores are a lot more inconsistent than Angela's scores, which means that his standard deviation is bigger. And in fact, it's a lot bigger, right? This is almost 10 times the size of Angela's standard deviation. So if you read statistics literature, standard deviation just is the standard way to measure spread. But keep in mind that as opposed to range, let me just go back to our calculation here, the definition of standard deviation is not intuitive. You don't just take the biggest number minus the smallest number. Okay, that's what we did with range. The definition of standard deviation is complicated. You have to take all of these deviations, you have to then square them, you have to then take the average of the squares, you then have to square root. Okay, so none of these things are particularly intuitive, right? Why are we doing all of this, you know? So there are several answers to that question. Well, why do we have to do this complicated thing? And the main answer is because, again, the range is a crude measure. The range just doesn't see what happens between the biggest and smallest numbers. The standard deviation, on the other hand, is not a crude measure. The standard deviation is a sophisticated measure of spread. And you pay a price in sophistication, and that price is having to do more complicated things. Okay, so the reason that calculating standard deviations is complicated is because the standard deviation is a sophisticated measure of spread. Okay, so here are a few things to keep in mind. The standard deviation of a data set is measured in the same units as the original data. That's nice. So if the data represents exam points, the standard deviation is also exam points. If the original data set is given in dollars, the standard deviation is also measured in dollars. Okay, so that's nice. It's pointless to compare standard deviations of data sets that are given in different units. Okay, so suppose that one data set is measured in miles and another data set is measured in feet. Then comparing the spread of those two data sets is probably not meaningful. You would first need to convert one data set to miles or one data set to feet. Make sure that both data sets have the same units. And then the standard deviations would tell you something. So as it says here, if you want to compare different data sets, you should have the underlying scale be the same. And if that's the case, then comparing standard deviations is meaningful. Okay, so for data sets that are based on the same underlying scale, so they're both based on feet, or they're both based on, test scores that go from 0 to 100, or whatever, then a comparison of standard deviations can tell you something about the data spread. If the deviation is small, you can conclude that they're bunched together. The data is bunched. But as I pointed out a few times now, as the standard deviation gets bigger, the more spread out the data gets. Okay, so in particular, again, if you see real-world data ever, generally the standard deviation is what is used to tell you how spread out the data is. Okay, so here we are concluding chapter 15. So let's just recap what we've done. In section 15.1, we looked at graphs and charts. Okay, graphs and charts are a visual summary of the data. So you don't just want to stare at a spreadsheet of numbers, right? It's hard to learn things from looking at raw data. So a pie chart or a histogram or a bar graph or whatever is a visual summary of the data. It allows you to just get a holistic picture of the data without staring at the raw numbers. Sections 15.2 and 15.3 give you numeric summaries of the data. So not graphs and charts anymore necessarily, although we did look at box plots. But now, if somebody gives you a spreadsheet of numbers, and there are, say, thousands of numbers in there, again, you will just go cross-eyed staring at this spreadsheet. It's hard to learn anything from staring at a large spreadsheet. But if now I tell you, oh, well, the mean of the numbers in the spreadsheet is this, and the standard deviation is this, and the median is this, and here's a box plot, suddenly now you have a feel for what the data set looks like. If I give you a mean or a median, you have some sort of idea where the data is centered. Although, again, mean and median aren't perfect measures of that because of outlier pool, outlier influence, and other things like that. But they give you some sort of feel for the data. And then I can say, oh, and the standard deviation is 20 or whatever, right? And now you have a feel for how spread out the data is. Okay, so all of these things that we've studied now allow you to take a data set that's maybe thousands or millions of numbers and make the data set manageable. Okay, a human being cannot just scan their eyes over thousands of numbers and understand what the data set is. So all the tools of chapter 15 allow you to sort of take a large data set and break it down into something manageable. So that can be a picture, or it can be a 5-number summary, or it can be a mean and a standard deviation. So all of these things are just tools for making data more digestible. And if you didn't have these tools, statistics would be impossible. Okay, you are essentially just left with raw data, which again, for large data sets, is not terribly helpful. Okay, so that's the conclusion of chapter